Today we're going to talk about limits at places where a function increases or decreases without bound. So what does that mean to increase or decrease without bound? Well, in basic terms, it just means it's going up towards infinity or it's going down towards negative infinity. The most common thing we'll see with this is we'll be talking about vertical asymptotes. You should all be familiar with vertical asymptotes, right? So we're talking about here in this case, the function 1 over x minus 2. It has a vertical asymptote at x equals 2. And we're going to write that over here. It's got a vertical asymptote when x equals 2. Because, well, if I plug 2 into that function, I get 1 over 0. And 1 over 0 we can think about as like infinity, because if we can't divide by 0, but if we divide by something really, really close to 0, a really, really, really small number, right, we end up getting infinity or negative infinity if it's a really small negative number. And that's why the function is going to be approaching infinity or negative infinity is what we're going to say. So we're going to use one-sided limits for these. So the first one we're going to look at is the limit as x approaches 2 from the left of the function 1 over x minus 2. Well, if we think about what's happening to this function as we approach 2 from the left-hand side, right, from the left-hand side, as we approach 2, that function starts going down rapidly towards, well, negative infinity. It's approaching that asymptote, but it's going down to negative infinity. So we'll just say that limit is equal to negative infinity. If we talk about what's happening as we approach 2 from the right-hand side, right now as we approach 2 from the right-hand side, we're just going up towards positive infinity. So we'll say that the limit as x approaches 2 from the right-hand side of 1 over x minus 2 is just positive infinity. And since the left-hand limit and the right-hand limit don't equal each other, one's negative infinity and one's positive infinity, the two-side limit cannot exist. So we'll just say that this does not exist. But what we're going to keep in mind here is that regardless of whether it's a positive infinity or a negative infinity, technically these limits don't exist because our original definition for a limit explicitly said that a limit only exists if the function approaches a real number. Well, infinity is not a real number, and therefore these limits, technically none of them exist. But for our purposes, I always want you to write negative infinity or infinity on the one-sided limits. And if they match up, then if they were both infinity, we'd say the two-sided limit is infinity also. But if they don't match up, if one's negative and one's positive, we'll just say it doesn't exist. And generally speaking, on the AP test and the multiple choice questions, they won't put does not exist for one of these. They would put infinity or negative infinity for it. So you got to get used to that. Anyway. All right, so let's take a look at another one here. This time we're talking about the function 1 over the quantity x plus 1 squared. So we're going to take a look at what's going on at x equals negative 1, or as we approach x equals negative 1. Now, why are we doing negative 1? Well, because if I plug negative 1 into this function, I end up with 1 over 0. That's what yields us a vertical asymptote, right? A constant over 0 is what's always going to give us a vertical asymptote. So as we look at what's happening as we approach negative 1 from the left, we can see we're going up towards infinity. And as we approach negative 1 from the right, we can see again that both of those are approaching infinity. So for both of these limits, we're going to say they are infinity, right? From the left, we're going up. We're increasing without bound, and from the right, as we approach negative 1, we're increasing without bound. And therefore, we can say that this limit is also infinity. Even though technically none of these three limits exist, we're still going to go ahead and call them infinity. And we'll do one more quick case here. This time we're looking at negative 2 over x minus 3, that quantity squared. And so if we look at what's happening at x equals 3, the place where our vertical asymptote is, as we approach 3 from the left, we can see we're going down to negative infinity. As we approach 3 from the right, we can see that we're also going down towards negative infinity. And therefore, we're going to call both of these limits negative infinity. and the two-sided limit negative infinity as well, because they matched up. Now, once again, I'm going to reiterate this. Technically, these limits don't exist. We just call them infinities or negative infinities to give ourselves an idea of how the function is behaving at this location of the vertical asymptote, right? This special place on the function. We just want to give ourselves an idea of how the function behaves so we know what it looks like. This will be useful for us, especially when we're asked to graph basically random functions in a couple units from now. All right. Now, a study of limits, of course, wouldn't be complete without a formal proof that a limit is infinity, or in that fact, a formal proof that it equals negative infinity, perhaps. Now, when we do our formal proofs on our previous limits, we were always talking about a delta epsilon proof. Well, for these, it's not actually a delta epsilon proof. We change the epsilon into an m. So this is just going to be, we're going to call this a delta m proof. Okay? So if we want to prove that a limit as x approaches a of f of x equals infinity, given some m value greater than 0, there must exist a delta such that if the absolute value of x minus a is less than delta, then f of x must be greater than m. So what's that saying? Well, that's saying that take some value m, right, that we think our limit might be at a, and prove that that for whatever delta we choose, our function is always going to go above m, no matter how large of an m we choose. I might say, okay, I think the limit is 1,000, let's say. And then I just need to show that, well, if I pick a delta that's close to a, my function is going to go above 1,000, right? Well, I need to be able to pick any m, no matter how large that m might be. So I might need to pick an m. Let's say I pick this m, which looks like a pretty big number, but really in the grand scheme of things, compared to infinity, is really small. I just need to show for this m that there is a delta, right, a range over here that is small enough that if I go and draw those vertical lines, my function still has values larger than this. So I need to show that no matter what, no matter how large of a value I choose, I can always find a range of delta values surrounding a such that the value of my function somewhere in that interval is more than the m that I chose, no matter how big of an m that I choose, right? And I don't have the formal definition written out here for showing that it's negative infinity, but if we're talking about a limit as x approaches a of f of x equaling negative infinity, we can kind of just flip this picture on its end and sort of treat it like, well, all we really need to do is have an m that's less than 0, and we need to show that for all this, our function would just need to be less than m, right? So we'll do one of these in a little while with it being negative infinity. But really, we're just kind of flipping the picture on its end and saying, okay, pick some horizontal line y equals m and show no matter how large of a negative number that is, in other words, like negative 10 billion or something like that, show that our function on some delta range always goes below that value. So that's going to be our idea. These actually, I think, will end up being a little bit easier than some of the delta epsilon proofs that we did earlier in the unit. So let's take a look. We're going to do 2 or 3 of these today. And we'll note that a lot of these are going to end up being one-sided limits, just because, sometimes both sides of the asymptote, it's not behaving the same way. On one side, it might be going to infinity. The other side, it might be going to negative infinity, just as is the case with this one, right? If we want to prove the limit as x approaches 0 from the right of 1 over x is infinity, well, we're doing it from the right because we know what this function looks like, right? This is the function 1 over x. From the right, it is going up towards infinity, but from the left, it's going down towards negative infinity. And so it only makes sense. We wouldn't really be able to prove that it's infinity or negative infinity as we approach 0, because it's on one side it's 1, it's infinity, and on the other side it's the other, it's negative infinity. So we do it as a one-sided limit here, which actually is going to make things even less complicated for us. So let's see if we can do our proof here. Let's see if we can prove this is equal to infinity. So we're going to start with our given, and it used to be, right, epsilon, right, greater than 0, but now we're replacing our epsilons with m. So we're going to say given in m greater than 0, we need to choose some delta, and I don't know what that delta is, so just like before, we'll fill that delta in a little bit later. We're going to choose delta equal to, and then we're going to say supposing that we have we've got 0 is less than x, right? Because it's just x is approaching 0, so our x minus a is just 0. We can put this inside an absolute value here. I guess I'll do that for now, which is now less than delta. But I'm going to actually just say, okay, we don't really need that absolute value. And the reason we don't really need that absolute value is because what do we know about x? Well, x is approaching 0 from the right-hand side. Well, if we're approaching 0 from the right-hand side, that means x is positive. And if x is positive, then the absolute value of x is just x. So really what we're talking about here is just that 0 is less than x is less than delta. So we don't really need to worry about the absolute value because this is a one-sided limit approaching only from the positive side of 0. And then what we need to show, if we look back to our previous page, the thing that we need to show is that given all of this, f of x is always greater than m, right? That no matter what m we choose, our function always goes above that value. So, well, what's our f of x? Our f of x is just 1 over x. So, if we think about this, 1 over x, well, how do we go from this inequality into something with a 1 over x? Well, all we'd have to do is take the reciprocal. And we're just going to take a look at solely this piece of it. If I were to take the reciprocal of both sides, I get 1 over x and 1 over delta. And what happens with an inequality when you take the reciprocal of both sides of it? Well, you flip the inequality sign, which is just perfect for us here, because now we've shown that our function f of x is greater than something in terms of delta, which is what we wanted it to show. So all we have to do is just say, well, if this thing was m, if 1 over delta was m, then we could figure out a delta to choose, right? The delta that we would choose, that would tell us that delta should be 1 over m if we just kind of cross multiply there. So we'll do that. We'll choose delta to be 1 over m. And now when we put that in here, we're looking at 1 over x is greater than 1 over delta, which is 1 over, well, we just chose delta to be 1 over m. So it's 1 over m, which is m. And we've shown exactly what we were supposed to show. That given an m greater than 0, if we choose delta to be 1 over m, then supposing that 0 is less than the absolute value of x is less than delta, then our function 1 over x is greater than m, where m is 1 over delta, or delta is chosen as 1 over m. And that's the end of the proof for this one. Pretty straightforward. Let's take a look at another one. So, again, this one's a one-sided limit. So we're looking at the limit as x approaches 1 from the right of the function 3x over 4x minus 4. And we want to prove that it's equal to infinity. Now, I'm not going to bother to graph this. We didn't really need the graph on the first one. We don't really need the graphs of any of them. So let's just go through and start out our proof. Our proof's going to start out with our given, right? Our given that we have some m that is greater than 0. And we're going to need to choose some delta, which we don't know what that delta is offhand at the moment, but we'll figure it out as we go through. And we should start with 0 is less than the absolute value of x minus 1 is less than delta. But I'm going to immediately think about what's happening here. I'm talking about an x approaching 1 from the right-hand side. If I'm approaching 1 from the right-hand side, that means I'm looking at x values that are greater than 1. And in fact, I'm going to just kind of make a side note over here that x is greater than 1 because I know that in a little while, I'm going to have to use that fact. But if the x values are greater than 1, that means that what's inside of here is greater than 1. And if what's inside of an absolute value is greater than 1, well, then we can just eliminate the absolute value. And so I can say just from one little piece of this that I know that x minus 1 is less than delta. Right? And if I know that x minus 1 is less than delta, I'm going to use this same little fact over here because, you know, the last one we took the reciprocal. I'm going to do the same here. 1 over x minus 1 instead of less than is going to be greater than 1 over delta. We're just going to keep that off to the side as a little bit of a fact too, something that we're going to need to use in a bit. And the reason I'm doing that is we might notice that, well, down here in our denominator, we have 4x minus 4, which if I were to factor a 4 out of that is 4 times x minus 1 in the denominator. It begins to resemble this, right? 3x over 4 times x minus 1. Well, it's not the same as 1 over x minus 1. There are some good relationships that we should be able to develop between the two, right? So that's why I'm putting that up there for now. So now that we've got all this sort of like side work done that's going to help us out along the way, we're just going to go in and start with our function and show that our function is greater than m eventually. But it's going to be, you know, we're going to eventually show that it's greater than something in terms of delta, and then we'll choose the delta to make that equal to m. So our function, in fact, I think I'll do this in a different color now, just since we're kind of changing gears here. We've got 3x over 4x minus 4. And like I said, I'm going to just factor out that 4. So 3x over 4x minus 4 is the same as 3x over 4 times x minus 1. And now, well, I know that 1 over x minus 1 is greater than 1 over delta. So a bunch of stuff times 1 over x minus 1 must be greater than all that same stuff times delta. So we're going to say this is greater than 3x over 4 delta. And then I'm going to use this very convenient fact that I know that x is greater than 1. Well, if x is more than 1, 3 times something more than 1 is going to be more than 3, right? So I'm going to use this fact here to say that, well, that means that 3x is greater than 3. And if the numerator of a fraction is bigger, then that makes the thing bigger. So if I say this is just greater than 3 over 4 delta, that should be a true statement, right? Because 3 times something more than 1 is going to be more than 3. And now I've done the whole process I really need to do. I've shown that my function is greater than something that's all in terms of delta. And so now we just need to choose the appropriate value for delta. We know that we want m to equal 3 over 4 delta. Well, just cross multiply. That's going to tell you that delta needs to be 3 over 4m. Okay? And so we'll just choose delta equal to 3 over 4m. We can say this is equal to 3 over 4 times 3 over 4m. Now I think we should see that if we were to take the reciprocal of this 3 over 4m and multiply, we'd end up with an m in the numerator and then 12 over 12. We've now shown that f of x is greater than m, and we've then thus proven that this limit is equal to infinity. Hopefully not too horrible. All right, so now we're going to do one with a negative infinity here. So we've got a limit as x approaches 1 from the left-hand side of x squared over 2x minus 2 and we want it to be negative infinity. So, as I said when we were doing this, I didn't have the formal proof written out for negative infinity, but it's the same basic idea, except we want to choose an m that is less than 0, because we want to have some small m value, some negative m value, and show that our function goes below that. So we're going to say, given an m less than 0, we're going to choose a delta, which we're not going to choose yet, but we'll choose it along the way. And now we should know that we've got 0 is less than the absolute value of x minus 1 is less than delta. But if we think about this, what we've really got going on here is x values that are less than 1, right? Which means that that absolute value ends up being a negative when I pull it out of there. And I should be able to, I'm going to get rid of this greater than 0 part, but I should be able to sort of rewrite this in saying that I know that that x minus 1 is going to be a negative number, right? Because as x approaches 1 from the left-hand side, I know that x minus 1 is going to be less than 0 because the values of x are less than 1, right? And so something less than 1 minus 1 is negative. But I should also be able to say that this is now then greater than negative delta, right? And that's actually how we would undo, like we did back with our absolute value inequalities. But if I were to undo just absolute value x minus 1 is less than delta, I'd end up with the x minus 1 in the middle, saying x minus 1 is greater than negative delta and less than positive delta, but I can put an even larger constraint on that and say it's less than 0 because, well, I just know that based on the fact that if I take something smaller than 1 and subtract 1, I get something less than 0. So we're going to be right here with negative delta is less than x minus 1 is less than 0. And from that, I'm going to just ignore the less than 0 part. Really, I'm just going to say, well, in fact, I'll do this right over here. I can do my reciprocal thing again. 1 over x minus 1 must then be less than negative 1 over delta. Right? I had x minus 1 was greater than negative delta, so if I take the reciprocal of both of them, it needs to become a less than, right? So I've now got 1 over x minus 1 is less than negative 1 over delta, or 1 over negative delta, however you feel like saying. So now we'll start with our function here. So our function is x squared over 2x minus 2, which is, of course, the same as x squared over 2 times x minus 1. And the reason I'm factoring out that 2 is because, well, I know something about 1 over x minus 1. So if I have an x minus 1 in the denominator there, I should be able to logically make the leap, right? I know that 1 over x minus 1 is less than negative 1 over delta. Therefore, a bunch of stuff times 1 over x minus 1 must be less than all that same stuff times 1 over negative delta. So we've now shown it's less than something, but not fully all the way there yet. Now, let's think about the rest of this. The 2 doesn't really matter. The 2 is fine there because as long as I can show that my function is less than something that's all in terms of constants and deltas, right, then I'm good. But I still have this x squared there. So I have to think about what's going on with the x squared. How can I somehow show that x squared is less than something else? Well, what is it that I know about x? I know that x is approaching 1 from the left-hand side. And so I know that it's less than 1. And if we're thinking about a limit, when I think about a limit, I'm thinking about approaching from a very close value as I approach 1, right? So let's just say we've kind of got a constraint on here that makes sense because we're doing a limit where x is going to be more than 0 but less than 1, because I'm not really approaching 1 unless I'm more than 0. So if this is a true statement, then it should follow that x squared is still less than 1 and also still greater than 0. And if I know that x squared is between 0 and 1, well, that means that I know for sure that it is less than 1. And so I could just make this logical leap that this is less than 1 over negative 2 delta, right? Because x squared is less than 1. And if the numerator of a fraction gets smaller, I should have a smaller thing, right? X squared is smaller than 1, so x squared over negative 2 delta should be smaller than 1 over negative 2 delta. And from there, I should now be able to say, well, I just want that thing to be m. So let me change to a different color here for a second again. If I let m be negative 1 over 2 delta, with just a little bit of cross multiplication, that tells me that delta should just be negative 1 over 2m. So we'll just say, okay, this is equal to 1 over negative 2 times negative 1 over 2m. And if you undo all of that, the negatives cancel, the 2 over the 2 cancels, and you have 1 over m, which is just m. Therefore, we just need to choose delta to be equal to negative 1 over 2m. And we can show that this limit is equal to negative infinity. I think that's it for the delta m proofs that we're going to do for limits that equal infinity. We're going to come back to delta epsilon proofs when we look at limits as we approach infinity, but that will be tomorrow, not today. So what we're going to do the rest of the day today here, just a few more problems. We're going to take a look at some fairly straightforward ones where we're not doing proofs, we're just trying to find the limits at the asymptotes without looking at graphs. And so we're going to kind of explore a little technique for how to do that. And it shouldn't be too bad. So you should be able to look at this function, f of x equals 1 over x minus 4 to the third power, and tell me that this must have a vertical asymptote, and it must be at x equals 4. Because if I plug 4 into it, the denominator is 0, but the numerator is not 0. So we're going to look at the one-sided limits at x equals 4, and then also the two-sided limit there to see if it exists. So we'll start with a limit as x approaches 4 from the left-hand side of f of x. So if we think about this, what we're going to do is we're just going to kind of intuitively think about this. If we approach 4 from the left-hand side, that means we're plugging in something like 3.99999999999. Well, 3.999999999 minus 4 is just going to be a really small negative number. So we end up with something like 1 over a small negative, very small negative, and this is really technical here, right? A really small negative number that's then being cubed. Well, if you take something that's really, really small and negative, and you cube it, you get something that's even smaller, right? Like if you cube 0.0000001, you get like 0.000000000000000000001. Probably didn't have the right number of zeros, but you get the idea. And it's still a negative number, right? Because a negative times a negative times a negative is a negative. So this ends up being 1 over, real technical here, we're going to say an even smaller negative number. And if I take 1 and divide it by an exceptionally small negative number, well, that just becomes an exceptionally large negative number. And therefore, this is going to be negative infinity. And so you should be able to kind of think this process out in your head. Just think, okay, what happens as we approach 4 from the left? Well, it's 3.99999. That minus 4 is a real small negative. Cube a real small negative. It's still a real small negative. And 1 divided by a real small negative is a real big negative. we're going to use the same thought process for a limit as x approaches 4 from the right. Now, instead of plugging in 3.99999, we're going to plug in 4.00000000001. Well, if I take 4.000000001 and subtract 4, I get a real small positive number, which I'm still cubing. And if I cube a real small positive, I get an even smaller positive. And if I take 1 and divide it by a really, really infinitesimally small positive number, I get an infinitely large positive number. And our limit as x approaches 4 from the right of f of x should be infinity. And you can check this on your graphing calculator if you want to graph this. You'll see that as you approach 4 from the left, it's going down. It's decreasing without bound. And the same from the right, it's increasing without bound. And therefore, our limit as x approaches 4 of f of x does not exist, because from the left it was negative infinity and from the right it was positive infinity, and those just are not the same. And again, remember that none of these actually technically exist, right? Limits can only exist if they are approaching a real number. So I think we'll do 2 more of these, and I think that'll probably be good for today. Let's look at this one. This one we should be able to look at 1 over x minus 2 to the 4th and say it has a vertical asymptote when x equals 2. Right? So we're just going to look for a limit as x approaches 2 from the left of f of x. And we're going to look for a limit as x approaches 2 from the right of f of x. And then we'll make a decision about the limit as x approaches 2 of f of x once we've done both of those. So from the left-hand side, what do you think about something like 1.999999999? Well, that ends up giving me 1 over a very small negative being raised to the 4th power. Well, if you take a real small number and you raise it to the 4th power, it's still real small. And if it's a negative number to begin with, a negative times a negative times a negative times a negative, right, an even number of multiplications there with a negative is going to give you a very small positive number. And 1 over a small positive number is just infinity. And likewise, with 2 from the right, we end up with 1 over a small positive being raised to the 4th power, because if we plug in 2.0000001 and subtract 2, that's a real small positive. And if we raise a real small positive to a power of 4, you get still a real small positive number. That's an even smaller positive number. And when you do 1 divided by that, you get positive infinity. And therefore, since the left-hand limit and the right-hand limit were both infinity, we can then say that the 2-sided limit is also equal to infinity. Even though technically none of these 3 limits exist, we're just going to use infinity to sort of give us an idea of how the function behaves. All right, here is our last one for today. So we're going to look at the limits at the asymptotes here. So first we have to find the asymptotes. I'm going to factor out that 4 in the numerator just to see that x minus 1. And then potentially that may cancel out with something in my denominator. So we got to factor that denominator. If I factor out that denominator, I end up with x minus 1 times x minus 3. And so I could see that this function has an asymptote, a vertical asymptote at x equals 3, but it does not have a vertical asymptote at x equals 1, right? Because the denominator and the numerator both have a factor of x minus 1 in them, which would cancel out. It would give us a hole in this function at x equals 1. So all we're going to worry about is the vertical asymptote at x equals 3 and see if we can figure out what's going on there. So we'll start with our limit as x approaches 3 from the left of f of x. So if I'm approaching 3 from the left, that's like plugging in 2.999999999. Well, these 2 terms right here if x is like 2.999999 are just going to cancel out. So really all I'm left with is 4 over 2.99999999 minus 3, which would be a real small negative. A positive 4 divided by a real small negative is going to be a negative infinity. And if I look at a limit as x approaches 3 from the right of f of x, well, the same thing's going to happen if I plug in 3.000000001, right? These x minus 1s can still cancel out, and I'm just left with 4 over a very small positive. Well, that's just going to be a very large positive. And then we should be able to say that since the limit from the left was negative infinity and the limit from the right was positive infinity, the limit as x approaches 3 of this function does not exist. Just like both the left and the right-hand limits technically don't exist, but we'll call them negative and positive infinity. But our two-sided limit, we cannot say anything about it other than it does not exist. So that's it for our limits as the function increases or decreases without bound as we're approaching asymptotes. Next time we're going to take a look at what happens as we have a limit when we approach infinity or when we approach negative infinity. In other words, we're looking at the in behavior of the function. But that's it for today. And we'll explore the other stuff next time.